Hello everyone, welcome back to my channel. Today we're going to talk about fluid mechanics, this problem. Water with a density rho flows downwards to a circular pipe of radius r and length L. The water enters the pipe with uniform speed v, but leaves with an axisymmetric parabolic profile with zero speed at radius r. That is, that means that the speed at radius r is equal to 0. That is our boundary condition, one of our boundary conditions, and a maximum at the center line. That is, the speed at r equals 0 is a maximum. Assume the pressures at the inlet and outlet are atmospheric. Determine an expression for the exit velocity profile in terms of a subset of rho, R, L, G, and V. Determine the force the pipe walls exert on the water to produce the given velocity profile. Clearly indicate the assumed direction of this force. Express your answer in terms of a subset of rho, R, L, G, and V. So to begin, we define our control volume. Um, yes. So the water entered the pipe with uniform speed V, but leaves with a different kind of speed. So this is our control volume. The volume, the water is entering it at speed v and leaving at speed ur. And so our conservation of mass equation, looks like this: d dt integral of control volume times rho dv plus the integral over the control surface of rho times u relative times dA, and this is equal to 0. Um, so notice that this is steady state since no volume is accumulating in the control volume. That is, the volume of the control volume isn't changing at all. The volume in the control volume isn't changing at all. So for steady state, this term goes to 0, because essentially this term means the rate of mass accumulation in the control volume, and that is 0, since there is no change in mass in the control volume. So now what we have to find is the value for integral of the control surface times rho times u relative dot dA, and this must be equal to 0. So we note that we have two places where there is velocity entering the control volume, and our control volume is a cylinder. It's basically a cylinder. This is our control volume. This is corresponds to this face, and this one corresponds to that face. And dA will be the vector orthogonal, or the vector defining the area of each of these two faces. So basically the volume entering will have to equal the volume exiting in that case. And this is what the control surface tells us. Um, so we know what the mass flow rate is for this velocity over here, since it is evenly distributed velocity profile. And we can represent it as basically, let's just quantize this as V in, and then this is V out. Uh, and quantify it as such. So V in is going to be equal to um V, which is the U relative, rho V, and then dot dA. dA is going to have it's going to point opposite the direction of the velocity flow. So this is actually going to be a negative value. So negative rho V multiplied by the surface area of the control surface, which is pi r squared. So pi r squared. Because we are taking the control volume to be at r squared. Yes. So, and then we are gonna have to add the flow outwards. Um, And this is where it gets tricky. Basically, we are given that this velocity profile is parabolic. And what it means by parabolic is that the general form of the equation can be written uh as mm, AR squared plus BR plus C. That is what a parabolic general equation is. And it can be represented as the and is it going to be positive or negative? First of all, let's ask that question. Well, the velocity vectors are pointing in the same direction as this area vector, so it's going to be positive. And we're going to integrate. We're going to have to integrate actually. From Yes, so this is something that we're going to have to integrate. We're actually going to have to apply this integral for once. Um, it's going to be integral from some bounds of rho times the relative velocity, which is going to be this parabolic equation over here, which is AR squared plus BR plus C. And dA. So what is dA going to be? And dA is going to be basically this area, uh, but we're taking small small areas of this surface area. So this is a circle. We can divide it into differential elements with concentric circles. So this is a differential area. We can call it dA, and it has a differential radius of dr, and dA is thus equal to this portion is r, as we see over here. This portion is r. Yes, so it's going to be the circumference of this circle, which is 2 pi r, times the thickness of this strip, which is dr. Another way we can do it is we can actually note that the area of the circle is going to be pi r squared, and then we can differentiate both sides to get the differential element as 2 pi r dr. Both methods are valid to get the differential area. Yes, so now we plug this in for dA, so 2 pi r dr. Now we have to find the constants A, B, and C. And we can do this using the boundary conditions that they give us. Basically, we're given that since UR is equal to AR squared plus BR plus C, and we're given that it has zero speed at radius R equals uh big R. Mhm. So we at least know one condition, and that is that UR is equal to 0 is equal to AR squared plus BR plus C. And it's also maximum at the center line. And this is helpful because at the center line, it's maximum, which means that the slope is actually 0 there. In a parabolic distribution, when it's maximum, the slope is 0 at that point. And this means that the derivative of UR with respect to dr is going to be equal to 0 at that point. And we can definitely use that to our advantage. Basically, dur dr is equal to 2ar plus b. This is equal to 0. Um, yes. The maximum occurs at the center line. Wait, sorry. The maximum occurs at the center line, which is when r is equal to 0. Yes, r is equal to 0. So let's plug in r equals 0. So 2a0 plus b is equal to du0 at dr, which is equal to 0. Basically, the slope at that point is equal to 0. So b is equal to 0. So with this new information, we can plug b equals 0 back into this equation to get ur is equal to 0 is equal to ar squared plus c. And from here, c is equal to negative ar squared. So plugging all these into the equation for ur, we have ur is equal to ar squared plus 0 times r plus c, which is negative ar squared. So we get that ur is equal to a times r squared minus r squared. Now we can plug this form back into our conservation of mass equation, which is over here. Because we have simplified it sufficiently. Basically, we have reduced this equation, which is ur, into just this equation over here. So from conservation of mass, we have cs rho u relative dot dA equals 0 is equal to negative rho times v times pi r squared plus integral of rho a r squared minus r squared 2 pi r dr. And we integrate it from 0 to r since that is the surface area of our control surface. It spans from 0 to r. So 0 to r it is. And let me see. There are probably some things we can factor out or even get rid of. Basically, we can cancel the rho by dividing on both sides by rho. And we can also get rid of the pi on both sides. So this simplifies further to now negative v r squared plus 2a times integral from 0 to r of r3 minus r squared dr. And don't forget that this equals 0. So then vr squared is now equal to 2a times r r to the power of 4 over 4 minus r squared over 2. Is that correct? let me see. So yeah, so oh okay, they simply evaluated it already. Yeah, so we have r squared times r squared over 2 evaluated from 0 to r. And this is equal to 2a r4 over 4 minus r4 over 2. And this is in turn equal to negative 1/2 a r to the power of 4. And thus a is equal to negative ar to the power of 4 over 2 over 2. Which is, wait, no, actually a is equal to vr squared over negative 1/2 times r to the power of 4. So this is equal to negative 2v over r squared. So we can thus write the velocity profile at the exit as um, u r is equal to, now we have all the constants. We simplified it to a times r squared minus r squared. And we now just found that a is equal to negative 2v over r squared. So negative 2v over r squared times r squared minus r squared. Or simplifying it further, we have this is equal to negative 2, or it's equal to 2v times r over r squared. Wait, sorry. 1 minus r over r squared. So that is our equation. And let me see. Yes, part A is done. And now for B, we have to determine the force the pipe walls exert on the water to produce the given velocity profile. Clearly indicate the assumed direction of this force and express your answer in terms of a subset of rho, r, l, g, and v. So, how can we go about solving this problem? We know that this will probably, in my mind, I'm thinking this will probably be conservation of linear momentum, because conservation of linear momentum states that change in momentum will result in a net force. So we can relate this change in momentum to the net force that the pipe walls exert on the water to produce this given velocity profile. Sure enough, conservation of momentum is a direct consequence of Newton's second law, which states that the net force on an object is equal to its rate of change of momentum, or F equals dp over dt. If the net force on a system is zero, then its momentum does not change. It is conserved. This principle applies to closed system where no external forces are acting, meaning the total momentum of all objects within the system remains constant. Newton's second law as a foundation for momentum conservation, as you see over here. Now let's look at the conservation of linear momentum equation that we will have to use, and that is this equation over here, this is the conservation of linear momentum equation. So sure enough, we see that it results in a net force. So uh, basically, Fs are surface forces like shear forces and pressure forces, which is probably what we're interested in here since we're interested in the force exerted on the water by the wall, which will create a pressure, and also body forces like gravity. So another thing to note here is that the linear momentum equation has this acceleration component, and that is if we consider it from a non-inertial reference frame. But over here we are in an inertial reference frame, so we don't have to worry about this component since the structure isn't moving. So the control volume is fixed. So a non-inertial reference frame control volume refers to a control volume where the fluid or system being observed is within an accelerating or non-inertial coordinate system, such as one rotating or linearly accelerating. Unlike the Eulerian frame, a fixed inertial control volume, applying conservation laws like the momentum equation in a non-inertial frame requires adding fictitious or pseudo forces, like Coriolis or centrifugal forces, to account for the frame's own acceleration to accurately describe the fluid motion. So, yes. But in this case, our control volume is fixed, so we don't have to worry about that. Yeah, so over here, let's first write the governing equation. So the governing equation for conservation of linear momentum is going to be d dt of the control volume. And we're actually evaluating it in the z direction since, let me see. The linear momentum equation in the z direction. Let's see what that is. Sorry, or actually wait, let me see what it said even over here. It doesn't give us a coordinate system, so we're just gonna call this direction, I'm gonna call it XY. So Y is vertically downwards, but positive Y is vertically upwards. So yeah, control volume and then velocity in the Y direction times rho times dv plus the integral of over the control surface of uy and the rho u relative dot dA. And this is equal to the body force in the y direction uh plus the surface force in the y direction. So as we see again, because this is steady state flow, this term is zero. Um, and what about this term over here for the conservation of linear momentum? We don't have to calculate all of this again since we already calculated what this value is, I presume. Yes. Yes, we already calculated what that value is. So we don't have to calculate it again, but we do have to multiply it by this constant, which is uy, which is the velocity in the y direction. But first of all, let's ask ourselves, is that actually constant? So, but I also have bad news. It's not constant. So we are gonna have to integrate again. And basically this uy term is going to be the velocity at the exit, I think. Or at least it's not all going to be, but basically for the first one, because this control surface is split up into two parts, we have one type of flow over here, we have another type of flow down here. So for the entry point, we found that it's equal to rho v times pi r squared. So now there's just going to be an additional v term since that is the velocity going in. And that velocity is actually pointing downwards. So we're going to do we're going to do basically, let me see. Yes, v times negative rho v pi r squared. Um, hold on. Yes, and then plus the integral from r equals 0 to r equals r. So from 0 to r of ui at the exit, which is given by this equation over here, which is ur. The integral of 2v times 1 minus r over r squared times times let me see, yes. So times rho and then times another 2v times 1 minus r over r squared. And then times uh 2 pi r dr. Yes. So this is this is then going to be equal to the let me see. This is then going to be equal to the weight of the fluid, which is going to be uh first the rho times the volume because rho is mass per volume. So rho times volume of this control volume will give us the mass inside, and then mass times gravity will give us the weight. So it's going to be equal to, and this is going to be the body force, which is gravity. So it's going to be equal to pi r squared first. Times L. And then that is the volume, and then we multiply it by rho and then by g. So rho g pi r squared L, and then the basically this component is the surface forces due to viscous forces or pressure forces. And the pressure force is going to be from the wall, and we're going to call it F wall. So F wall. So let me see. Yes, because the wall probably has some like viscosity against the water and the wall. And there's also basically the pressure that the wall exerts on the water that causes it to flow. Yeah, this looks like a very long, complicated equation. Yeah, so we have to simplify this whole equation now, which will be the hardest part. We might need more room. So, okay, this whole equation is equal to negative rho v squared pi r squared plus mm, let me see, so we have 3, 2, so 2 times 2 times 2 is 8. And then we have pi, and then we have rho, we have v squared, and we integrate from 0 to r of I believe r minus 2 times r cubed over r squared plus r5 over r4 dr. And wait, hold on. Sorry, I wrote it wrong. So supposed to be this okay, and then we have 1 minus r over r squared r dr, and this is equal to what we said over here, which is the weight, which is rho g pi r squared L minus the F wall. So F wall, we can thus write F wall as equal to uh rho g pi r squared L plus rho v squared pi r squared minus 8 pi rho v squared integral from 0 to r of 1 minus r over r squared times r dr. Um, and actually, we can further simplify this expression inside to be r minus 2 times r3 over r2 plus r5 over r4 dr. And simplifying this further, I'm going to speed up the process now. You will get that F wall is equal to rho g pi r squared L plus rho v squared pi r squared minus 4 over 3 p v squared pi r squared. And F wall is going to be equal to rho g pi r squared L minus 1 over 3 rho v squared pi r squared. And so F wall is assumed to act upwards in the free body diagram as well. So just keep that in mind. Um, yeah, so let's do a quick recap of this problem. Basically, we were given that the volume enters in and then when it exits it has a parabolic distribution. And this parabolic distribution we knew the general form, but we did not know the three constants A, B, and C. To find these three constants, we needed three equations: the two equations from the boundary conditions and conservation of mass equation. And then we solved for these three constants and we found the equation for the exit velocity profile in terms of some variables. And then for part B, we applied conservation of linear momentum in order to find the force that the wall exerts, um, the force that the pipe walls exert on the water to produce this given velocity profile, the given velocity profile. And basically, because if there was no forces applied by the pipe on the water entering in would have the same distribution as the water exiting out. But because of some forces, like shear forces and pressure forces, but maybe, and also from the gravity of the water itself, the velocity profile of the exit is different, is of a different distribution. So we use conservation of linear momentum in order to find that force applied in order to produce this given velocity profile. And for that part, we had to note that again that this is steady state flow, so this goes to zero. And we also had to know to include the gravity and how to solve for the force at the wall. And another thing we had to know is that this is in an inertial reference frame, so we didn't have to use the other term that we needed for the non-inertial reference frame. So yes, this problem is quite involved, but I hope that it helped you guys with your understanding. See you guys in the next video, and I'm going to post this video online as well as the solution slides. Thank you so much.